On the evening of December 28, 1879, the train from Bern, Thailand was expected in Dundee. It had crossed the Firth of Tay hundreds of times. The bridge had been open for nearly 2 years. The crossing was routine. The train did not arrive. A man named John Watt was watching from the south cabin when the train entered the high-girder section. He saw a flash of fire, then a shower of sparks, then darkness where the lights of the train should have continued across the Firth and reached the far shore. The Firth of Tay swallowed the rest. The public remembered the storm. The metal remembered something else entirely. The inquiry said the Tay Bridge fell because of a gale. The bridge's own maintenance record says the storm was only the last load applied to a structure that had been telling the truth about itself for nearly 2 years. Nobody was listening. That is the case this reconstruction is making. Not that the gale was harmless, not that the inquiry was wrong, but that the storm arrived at a bridge whose stabilizing system had already been degrading since opening day, and that the evidence of that degradation was there in the maintenance logs, in the inspection conditions, in the design correspondence, in small pieces of metal inserted into joints that no longer fit. The packing pieces were the warning. The storm was the cross-examination. Here is what the record actually shows. The bridge that crossed the Firth of Tay was, by the standards of its time, an argument about what engineering could do. The Firth is wide, the water is cold, and the wind had a long, exposed reach across the open water before it struck the high ironwork. Building a railway bridge across it meant committing to long spans, tall columns rising from the riverbed, and a high girder section that carried the track above the shipping channel at height. A span, to be plain about the term, is the distance a structure must carry between fixed support points. The longer the span, the more the structure must resist not just its own weight in the weight of passing trains, but the force of wind pressing against it from the side. For the Tay Bridge, the high girder spans were the most exposed portion of the structure, and their dimensions were not short. The inquiry material recorded lengths of 245 feet and 227 feet for the principal sections. Those dimensions are not technical decoration. They are the beginning of the problem. In 1869, before the bridge was built, Thomas Bausch put a formal question to Major General Yolland. Did wind pressure need to be calculated for open lattice girder bridges? The answer Bausch received was that for open lattice girders up to spans of 200 feet, wind pressure did not need to be treated as a separate consideration. 200 feet. That was the condition the answer depended on. The bridge Bausch then built had high girder spans of 245 feet and 227 feet. Both exceeded the boundary the 1869 correspondence had set. The condition under which the wind pressure question could be set aside was gone before a single high girder was raised. But then there is another problem. Whether anyone connected the 1869 answer to the changed dimensions during design and construction cannot be confirmed from what survives. The gap between those two facts, a boundary established in correspondence, a bridge built beyond it, sits in the record without a documented bridge between them. What is not in doubt is the consequence, a set of high girders whose resistance to lateral force had never been formally calculated for the spans that were actually constructed. A bridge does not only carry weight downward. On the Tay, the deadliest force came sideways. Gravity is vertical, wind is lateral. A bridge without a formal calculation for lateral loads may perform acceptably in calm weather, in moderate wind, in the range of ordinary use. The question is what happens when the lateral load reaches the scale the Firth of Tay could supply on a winter night. Bausch was working within a professional culture that trusted certification, trusted precedent, and trusted the evidence of a bridge that had opened without incident. By those standards, he had ground to proceed. But the 1869 correspondence carried a limit. The bridges built had crossed it. The numbers are in the inquiry appendices. Major General Hutchinson carried out the inspection before the bridge opened to passengers. He passed it. That is the fact the popular memory kept. What the popular memory dropped were the conditions attached to his passing verdict. Hutchinson wanted the bridge inspected again during high wind. Not as a formality, as a substantive test. He was not satisfied that the behavior of the structure under the stresses a gale would impose had been adequately demonstrated by the inspections he had been able to conduct in the weather conditions available to him. He also imposed a speed restriction. Trains were not to cross at more than 25 miles per hour. The high wind inspection he requested was never conducted before December 28, 1879. What would that inspection have found? The record does not answer that question, and this reconstruction will not pretend otherwise. The record only says that the test was deferred, that the man whose job was to certify the bridge for public use looked at what he had in front of him, passed it, and then noted in writing that there was something he still needed to see. And this is where the record gets uncomfortable. The storm that arrived in December 1879 was, in a sense, the test Hutchinson had asked for, and that no one had arranged. The bridge met the high wind examination without any prior preparation an inspection would have supplied. It met it carrying 2 years of use in its joints. At the north end of the bridge, signalman Thomas Barclay occupied a post that gave him a different kind of knowledge than the inquiry's post-event calculations. He was not writing engineering analysis. He was watching the bridge work. Barclay was present at the structure on the days between inspections, the ordinary days, the unremarkable crossings, the winter mornings when wind came off the water and the bridge took it. His testimony to the inquiry described what he had heard and seen from his position. The movement and sound of the structure in windy conditions, the accumulated impression of a bridge under repeated stress across months of daily observation. What Barclay reported was not structural analysis, but it was not nothing. It was the record of someone close enough to hear what the bridge was becoming, observations that mattered later precisely because the collapse would turn on lateral stability. His evidence went into the inquiry. The point here is that the bridge had witnesses whose access was daily and direct. People whose knowledge of the structure came not from formal assessment, but from simply being there while it worked, in all weathers, across all the months between opening and collapse. Whether that daily knowledge was sufficient before December 28th to name what was happening to the bridge is the question the record does not resolve. Opening day proved the bridge could stand once. It did not prove the bridge would keep standing as its joints shifted, its tolerances relaxed, and its fastenings began carrying loads differently than they had when new. A bridge is not a static object. After construction, its joints bed in under repeated loading, its bolts relax. Its connections begin to move in ways that inspection on opening day cannot predict and cannot certify forward in time. For a structure relying on a system of lateral ties and cross-bracing to resist wind force, this is the central concern. Cross-bracing is a system of diagonal members connecting the upright elements of a frame, intended to prevent the frame from racking sideways under lateral pressure. The diagonal members do their work only if their connections are tight. A slackened tie is not the same structural element as a tight one, and slack means the structure moves before resistance begins. Maintenance can address these changes. It can also inadvertently conceal how much the structure is changing. When a component keeps working loose and keeps being tightened, the maintenance log may look like routine upkeep rather than a symptom. The question of why a component keeps loosening is a different question from how to tighten it. There is no evidence the second question was formally asked before December 1879. Then the inquiry found something small, not a collapsed span, not a dramatic eyewitness account of structural failure in progress. Something smaller than that, and in some ways more damning. Thin pieces of metal inserted into joints, packing pieces. A packing piece, in structural terms, is a thin plate of metal inserted into a joint to take up a gap that has opened between surfaces that were originally fitted together. It compensates for looseness. It restores contact between elements that have shifted apart. The inquiry appendix observed that the introduction of packing pieces showed a considerable slackening had taken place in parts of the bracing system since the bridge entered service. Consider what this means as a structural record, not just a maintenance note. The high girders were held in lateral position by a system of ties and bracing connections designed to specific tolerances. After opening, those connections had relaxed. The gaps requiring packing pieces were not gaps that were designed in. They were gaps that had developed while the bridge was in use. Iron that was meant to bear load and resist lateral movement had moved, and the movement was enough to require inserted metal to compensate. Each packing piece is an entry in the bridge's own history. It marks a location where the stabilizing system had changed since it was built. But here is the problem the record cannot answer. How many packing pieces were there? How were they distributed across the high-girder spans? Was their pattern denser in particular sections that would later fall? The inquiry appendix recorded that these pieces existed and noted what they implied about slackening. It did not produce a map. The distribution that would tell you where the bridge had degraded most was not assembled from the evidence available. The warning was not a letter on a desk. It was not a formal report filed with the railway company. It was the bridge itself changing shape under the hands of maintenance crews. Loosened ties, corrected gaps, iron being asked to explain why it no longer fit the tolerances it had been manufactured to. The bridge was speaking. The question is whether anyone was listening in the right register. In a modern engineering reappraisal published in 2002, Peter Lewis and Ken Reynolds argued that the 1880 court did not determine the exact collapse mechanism. Their analysis pointed to a process: lateral oscillations in the high girders under storm loading, defective joints, fatigue cracks propagating through the lugs connecting the bracing to the columns, and a progressive failure sequence in which each failed connection transferred its load to the next, until the next could not carry what it had been given. A lug, to name the component specifically, is a projecting bracket or ear of cast iron, used here to connect the bracing members to the columns of the high girders. A fatigue crack is a fracture that grows under repeated cycles of stress rather than from a single overload. A lug subjected to repeated lateral loading may develop a crack that extends incrementally with each cycle, remaining invisible and unfelt until it reaches a critical length. At that point, the remaining material fails under a load that an intact lug would have carried without difficulty. The failure is not dramatic in its accumulation. It is quiet. It is invisible. It is the structure spending its reserve over time, a little at each cycle, until the reserve is gone. Lewis and Reynolds were explicit about one boundary: the precise initiation sequence, which specific connection failed first, cannot be determined from what survives. The pattern in the river is consistent with more than one starting point. The reconstruction stops there. The uncertainty is real, and the record does not resolve it. On the night of December 28th, the 4:15 from Burnasland left St. Fort Station at 7:08. The gale was from the west, striking the bridge roughly side-on across the exposed water of the Firth. That orientation placed the full lateral force of the storm against the face of the high girders, pressing on the columns, loading the bracing connections, tensioning or compressing the ties that remained in the positions they had been packing pieced into. The train entered the bridge. John Watt was watching from the south cabin. He saw a flash of fire, then a shower of sparks. Then the lights disappeared. The flash and the sparks are metal contact evidence, iron structure moving against iron structure in ways the design did not intend, components displaced from their positions and grinding against adjacent ones. Whether what Watt saw marked the beginning of the collapse sequence or a stage already advanced in it cannot be determined from his observation alone. His position in the darkness limited what he could see. What his testimony establishes is the location, the high girder section, and the character of what he witnessed. Not a bridge under manageable stress, but a bridge already in motion. The most cautious reconstruction is not a single catastrophic blow from the wind. It is lateral force meeting a stabilizing system that had been operating below its design tolerances for months, with connections that had been packing pieced, ties that had slackened, lugs that may have been accumulating fatigue damage through the repeated passage of trains in weather, until one connection failed and transferred its load to the next, and the next failed and transferred its load further, in a sequence that the storm did not create from nothing but that the storm was sufficient to complete. That is the likely mechanism. It is not confirmed. The record does not confirm it. It is the reconstruction that the physical evidence, the maintenance history, the 1880 inquiry findings, and the Lewis and Reynolds 2002 reappraisal collectively point toward when assembled against one another. At Dundee, the train was expected. It did not arrive. The absence was the first report. There was no dramatic announcement, no signal that came through the darkness saying the bridge had fallen. There was simply the scheduled time passing, and then more time, and then the recognition that the train had entered the bridge from the south and had not come out at the north. Communication between the two shores established this quickly. The bridge was searched by boat in darkness and in the continuing gale. What was found was water where the high girder spans had been. About 75 people were aboard the train. The record is careful about the exact number. What is beyond dispute is that the train and everyone on it entered the Firth of Tay when the high girders fell. The absence at Dundee was not a discovery in any dramatic sense. It was a clerical fact. A train had been expected and had not appeared. And the transition from that clerical fact to the scale of what it meant came slowly, through the searches by boat and through the eventual light on the water, showing wreckage where the bridge had been. The inquiry opened in early 1880 with broken metal, incomplete drawings, testimony from witnesses bounded by position and darkness, and a public that needed an explanation before the engineering questions were resolved. The room held fragments where a systematic record of the bridge's condition over its service life would have been useful and was not available. The court found the bridge to have been badly designed, badly constructed, and badly maintained, and that its fall was caused by the insufficiency of the cross-bracing and fastenings to sustain the force of the gale. That finding covered the essential truth. It also foregrounded the gale in a way that the structural deterioration evidence, taken alone, might not have done. The court did not speak in one clean voice. Yolland and Barlow signed one report. Rothery wrote another. Rothery's separate text pressed harder on Booch and on the maintenance regime than the joint report's language did. His version traced the accumulation of failure more directly. The design limit exceeded without compensating calculation, the inspection condition left unfulfilled, the maintenance record that showed the structure had been changing. The storm version, the gale against a weakened bridge, traveled further than Rothery's harder account, because everyone can picture a gale. Almost no one can picture a maintenance log. What the disaster changed in bridge practice was more specific than stricter wind calculations. The post-disaster analysis demonstrated that design assumptions, inspection conditions, construction tolerances, and maintenance practice had each contributed partial failures to a collective structural outcome. Before December 1879, these subjects could be treated as separate questions. After, the profession had evidence that a bridge could fail in the space between them, not because any one failure was alone sufficient, but because together, accumulated across time, they produced a structure that was not what its certification said it was on the night it mattered most. In the 2002 reappraisal, Lewis and Reynolds noted that the disaster led to important changes in bridge design, construction, and inspection practice. After Tay, treating wind load calculation as background rather than a central design question became much harder to defend. Inspection needed to address the structure as it aged, not only as it appeared on opening day. And maintenance patterns, the frequency and location of repairs, carried information about structural condition that no single inspection could supply. Whether Thomas Bouch deserved the professional destruction that followed is a different question from whether the bridge failed for reasons traceable to his decisions. Bouch died in 1880. The bridge he had designed was already gone. What remained was the record of what he had built and what that record said about why it fell. The record assembled from the inquiry's appendices and from the 2002 forensic reappraisal contains a design correspondence establishing a span-length condition for ignoring wind pressure, and a bridge built beyond that condition without a compensating calculation. An inspection pass accompanied by an outstanding requirement for a high wind test that was never conducted. A maintenance history documenting packing pieces that showed the bridge's stabilizing system had slackened measurably since opening, and a modern engineering analysis pointing to fatigue, cracked lugs, defective joints, and progressive collapse as the mechanism that translated storm loading into catastrophic failure. My read is that the modern reappraisal does not overturn the 1880 inquiry so much as finish a sentence the inquiry could not write. The court established that the bridge was insufficient for the force it met. What Lewis and Reynolds add is the material history showing how the bridge arrived at that insufficiency, not simply as a designed-in condition, but as a condition that worsened progressively through the loosening and degradation of the very system that should have resisted lateral loads. The inquiry named the result. It could not trace the sequence. The 2002 work does not change the verdict. It explains the mechanism behind it. One thing the record will not resolve: the first specific member to fail. The exact lug or bolt or connection that initiated the collapse sequence is not recoverable from what survives. That gap is permanent. A reconstruction that filled it in would be inventing, and this one will not. My verdict is that the storm did not murder a healthy bridge. It cross-examined a failing one, and the bridge answered in iron. The 1880 inquiry was not wrong. Badly designed, badly constructed, badly maintained, that verdict held the essential truth, reached in 1880 from the fragments that were available. What it could not do was trace the precise mechanism, the way fatigue cracks in cast iron lugs, loosened connections, and accumulated structural slackening had been reducing the bridge's lateral resistance across the months before the gale arrived, so that when the gale did arrive, it met something that had already been spending its reserve. The bridge had been recording its own deterioration in the only language available to it: small metal compensations for gaps that should not have been there, repeated maintenance at joints that should have held, a high wind test that was asked for and never arranged. None of these taken alone was conclusive. Together, they formed the sentence that the inquiry reached toward and could not quite complete. The storm was the last load. The packing pieces were the signature.